All right, this section is 12.5. And I think we're going to take a little bit of like an investigative approach to this idea. Okay, so I'm going to ask you some questions. How would you, if let's say I started at that point right there, and I wanted to get to, let's say, that point right there. Okay, how would you go from A to B if you were only allowed to travel like you know you travel in the coordinate plane? How would you go from A to B? Okay, so you'd either go up 5 and then right 4, correct? Or right 4 and up 5, correct? Okay, that's referred to, those are because any one of those motions that we make, if I go up 5 or over 4, go that direction, or I go right 4 and up 5, that direction, collectively, those two sets of directions create a rectangle for us, right? And we're moving, when we move left and right, up and down, and only using those movements, we are moving in what we refer to as a rectangular procedure, okay? So we call those rectangular, we call this point 4, 5 a rectangular coordinate, okay? You could also travel from A to B directly along that line right there, correct? And that would be moving at a radius, okay, or we call a circular movement. Sometimes they call it a modulus or a vector. Okay, we could talk about it that way. You'll see all those words later on in other courses. But when we move in a circular pattern, we call it polar coordinates. Okay, which you won't talk about polar coordinates until about this time of the year in trigonometry. But I'm going to replicate what you just told me. If I want to go from A to B, I'm going to go that distance there, and then let's see there. So just trying to create the triangle. Okay. All right, so what I've done here is just try to create this so that when I move that point E, you can still get those two distances to show up. That would be the direction, the directions or the pathway that you take to go from A to E. Okay. Now, because those are rectangular coordinates, okay, rectangular movements, that's a right angle right here at C. It's always going to be a right angle right here at C. Okay. What I've done is I have forced that distance right there to always be 5. Okay. So if I force that distance always to be 5, and I ask you, okay, how do I go from, what are the points that are, you know, point E, how can I identify point E, its location? We can use the Pythagorean theorem knowing that that's 3 and that's 4. We could take those numbers and square them, add them together, take the square root, and that's going to give me that number to be 5. Does that make sense? Okay. Because of the Pythagorean theorem, no matter where E goes, see if I can give you the name and value of E. So if it goes there, 3 and 4, use the Pythagorean theorem with that number and with that number as X and as or as A and as B for A squared plus b squared equals c squared, and it's always going to give you 5. If I go to that point there, it's going to do the same thing, okay? But even if I do it at that point, okay, and what I'm going to do down here is I'm going to say x times, or the x of e, I'm going to square that, plus then the y of e, and I'm going to square that. So what it's going to do is going to grab whatever that number is there, square it. Grab whatever number that is and square it. And that should give us 25, which is the hypotenuse squared, right? So I'm going to hit enter, and it does give me 25. And I just want to show that no matter where I move E, is that always 25? Okay. So as I'm moving E, okay, what I want to do is record its position of where it was. Okay? So I'm going to do this trace technique. And as I move E, okay, all of those points right there are satisfying the Pythagorean theorem. Okay? So we all got those right angles. If I keep doing this, no matter where E goes in either quadrant, and I trace all the possible positions of E, what do I end up tracing out here? A circle. Okay? So what that tells us is that a circle is defined by this triangle. It's defined by the Pythagorean theorem that we just went through. Okay? Basically what happens is this distance here, okay, we know, let's see here. We know that distance from there to there is found in the Cartesian plane. Okay? We've talked about this a lot. We talked about this really I think it was like the first day of geometry that we actually started talking about the curriculum. That we said that distance, let's just call this R for now, that R, okay, was equal to, let's just be very simplistic, R squared would equal A squared plus B squared, correct? Okay. Now, if you remember from what we talked about in that first couple days, we said that point right there, we were calling that x2, y2, actually let's call it x1, y1, doesn't really matter. x1, y1, we called this one x2, y2. And if I wanted to find the horizontal distance between those, okay, it was the difference in the x's. We would subtract those and square, and then the difference in the y's, right? Okay. Now, if I name this one, because we can be a little bit more applicable or accurate with what we describe this one as. If this one's x1, y1, isn't this one going to have this, because it's a horizontal line, isn't it going to have the same y value? So if I called that one y1, I could call this one y2, but it doesn't make sense to do that. I might as well call it y1. Okay? And if I want to find that distance there that we're calling A, it's just the difference between those. Because if I subtract the y's, that gives me 0. Okay? So what we end up with here is that A distance is x1 and x2's difference. So I'm going to say x2 minus x1. And then I'm going to square that. Okay? That is going to equal r squared. And then plus I got to find my b squared. Well, that b squared is now the distance between those. And if this point is x2, might as well keep that e coordinate as being described as x2. And now this was y1. Would you agree that this y value is different than y1? So I'm going to call it y2. And now if I subtract and do the distance formula on those, okay, or because I know it's a vertical line, that when I subtract the x's, that's going to go to 0. So this distance here is only defined by the y2 minus the y1, and I'm going to square that. Okay? Now, that is going to give us this radius. Okay? I'm going to be very generic here, and I'm going to say that this x1 and y1, that ordered pair right now is 0, 0. So let's replace this with 0, and let's replace that with 0. And when I do that, I get r squared equals x squared plus y squared. Okay? Now, let's talk about our specific question here. You remember how big I said that r was here? It was 5. So r squared would be 25. If I go 25 equals x squared plus y squared, okay? If I type that in as an equation, now that's what we call an implicit equation because x's and y's are together on the same side. Nothing to solve for. If I type in x squared plus y squared equals r squared, or in this case 25, does it graph a circle right on top of what we traced out? Does that kind of make sense? Okay. So the formula for a circle, the equation for a circle, comes from the Pythagorean theorem, and it comes from the distance formula. Because a circle is only defined, we talked about this the first day we talked about circles, the only dimension that impacts a circle and the size of a circle is its radius. And a radius is always going to be the hypotenuse of some right triangle in the coordinate plane. So knowing that connection, we get a circle from the Pythagorean theorem. We get the geometric equation for a circle from the Pythagorean theorem. So that is why we get the equation. I'll demonstrate this here in a little bit, but the equation for a circle centered at the origin, okay, the equation of a circle centered at the origin is always x squared plus y squared equals r squared. Okay? That's when it's centered at the origin. Now, because we can take any single function or any, it doesn't have to be because a circle is not a function. We can take any single graph that we ever come across and we can move it left, right, up, and down. Okay, we can stretch it. We can do all. They're called transformations. Okay, which we will talk about transformations next week. But if I want to move my circle, okay, so that its center is no longer at 0, 0, what we have to do, and I'll show you this in GeoGebra, okay, right now I've got a circle centered at 0, 0, and you see here that it's going to produce, it's going to show me what the equation is of that circle, okay. You see my radius is 2, so they square that and get 4 over here, right? If I want my radius to go to 3, they square 3, and it becomes 9, okay? This is ultimately a squared plus b squared equals c squared. Is that okay with everybody? Okay. But now if I want to move that thing to, let's just move it left and right, okay? Let's move it right first. If I move it to the right 2 units, and I center it now at 2, 0, that 2, the distance of 2, because it was along the x-axis, it gets put with the x variable, and because I move it to the right, what's going to happen, it's a transformation. I don't want to get into right now the algebra of y to minus, but if I move it to the right, it's going to be minus that distance that I moved it to the right. Is that okay with everybody? So if I want my x distance to be 3 or 4, okay, it would be x minus 3. x minus 4, x minus 5. You see how moving it to the right, however far I want to move it to the right, how that then gets mimicked in the equation. Is that okay with everybody? Okay. Now, what do you think is going to happen if I wanted to move it to the left? Turns into a plus. X plus 1, x plus 2, x plus 3. So moving left and right, you are going to, if I'm moving to the right, you subtract how far you're moving to the right. If I'm moving to the left, I'm going to add how far I'm moving to the left. Okay. If I wanted to go up, okay, up and down is attached to the y value, right? So if I want to go up, yeah, click on this tool. If I want to go up 1, you see then it goes y minus 1. So the 1, because I'm going up 1, is attached to the y value, but going up is subtraction in this case. Up 2, it's y minus 2. Up 3, it's y minus 3. Is everybody okay with that relationship? So if I wanted to go down, what would it be? Okay. Does that make sense? Yes. So it's counterproductive or counterintuitive, I guess is a better word, than what you would think. You would think moving to the right is addition, right? But in what we call transformations, that's the opposite. And the idea here is because our formula is actually when we move a circle in the coordinate plane, okay, and this is all predicated that x minus h is because initially when we were solving and coming up with the formula, it was like x2 minus x1 or x1 minus x2, right? So it's always minus some x value. So if I go minus like an x value of -2, what's x minus -2? Turns into x plus 2, right? X sub 2 plus 2. So if I wanted to go to a -2 on the x-axis, because of the minus that's already here from the algebra, from the geometry of the distance formula, it's actually going to be a minus a negative then, it turns into a plus. So that's why it's counterintuitive to what we think it should be, okay? Because minus a negative turns into a positive. I think that's why it's confusing. It's hard to think about. But this is the formula for every circle we ever come across, okay? If it's centered at 0, 0, you can see then that the h would be 0, and x minus 0 is just 0, y minus 0 is just 0, or y. Sorry, x minus 0 is just x, y minus 0 is just y. Square those, I get that. So that's the one centered at 0, 0, right? If I want to move it around to other positions, okay, let's say I want my center to be at the point 5, comma, -2. Okay, that is our h value. 5 is our h value. -2 is our k value. So we go x minus 5 squared plus then y minus -2 squared is equal to r squared. Okay? And what happens then is that turns into x minus 5 squared plus y plus 2 squared equals r squared. Let's say we had a radius of 3. So then right here would be, if r is 3, we would put 9 there. Okay? And that then would be the equation of a circle centered at 5, -2. So if I show you that, so I want the center to be at 5. Come on. And the y value to be at -2. And you see that that is what is produced when you have a radius of 3. X minus 5 squared plus y plus 2 squared equals 9. Yes? Yeah, so like visually, so C right here, that's the H and K. So that's the center of your circle. Does that make sense? And then this, so when I plug that into here, what that is going to produce, so if I say, if I choose a value for X and a value for Y and plug those in here, okay, that are on, so this formula here is an equation for everything on that solid black circumference. That's how I get those points. Let's say so if I take the point D, which is a 7.03 and 0.21, if I put 7.03 right there for that X, and I put 0.21 for that Y, and I subtract 5 and square that, add 2 and square that, and then sum those together, I will always get 9. So these points on here are the points that what we say satisfy this equation. Does that kind of make sense? H and K is always the center, yes. And the formula is always it's always X minus H and Y minus K. There's always subtraction there. What we can do then, and this is just explaining, this is when I didn't have GeoGebra explain that stuff, but we're seeing the distance formula, the length of that right there can be found using this. If I change so let's just call, if I were to call this like X2, Y2, and this to be X1, Y1, and I plug those, so where I see X2, I call it X, and where I see X1, I call it H, I would get X2 minus H, that quantity squared, plus Y2 minus K, that quantity squared. So it's just a redefining of my variables, and that will equal, so I'm going to square both sides here. That gives me distance squared. So that's another way of redefining my variables to find that distance right there. Does that make sense? Okay. Now, usually what would happen then, it's because I've redefined X1 and Y1, they don't exist anymore. I call them H and K. So there's no need to have X2 and Y2 anymore. Might as well just call those X and Y. So then up here in my formula, I get X minus H squared plus Y minus K squared. Instead of calling it D for distance, let's be more appropriate with what that distance is. It's the radius of a circle. So that's maybe another way of viewing where that formula comes from and why it's X minus H and Y minus K. So once we have that, and basically what you need to know for the end of course exam when they present this type of stuff to you, if they do, they have in the past, is that my formula is X minus H squared plus Y minus K squared equals R squared. This is H, and that's K. Okay, it's alphabetical too. That might be a way to remember, because some people in the past get them confused. Okay, no textbook will tell you this, but a lot of structures that happen in mathematics, whether intentional or not, in remembering like how I fit a set of information to a formula, a lot of times they're alphabetical, especially. They're alphabetical when they're showing up in the ordered pair, and then they're alphabetical in how you put them in here. Does that make sense? Okay. So here, since H is 5, I'm going to go X minus 5 squared, and then Y minus K. So K is negative 2, so this minus sign is always a minus, so it's minus a negative 2. My radius is 7, so we'll square that. And then I always go back and say, okay, well, minus a negative becomes positive, and that's the logic of why there is Like if I wanted to go to a center that was below the x-axis, so a negative y value, why it turns into a positive in my formula. Why it's y plus 2 instead of y minus 2. Is that okay with everybody? So that is our formula for that particular circle. Now, what's nice about like all your graphing tools that you can use, now you won't have the graphing aspect on the end of course exam. The end of course exam only gives you guys this calculator here. Okay, so there's no graphing. But in your homework and stuff like that, I think it's important to be able to graph this stuff. And Desmos is what we call an implicit graphing calculator, okay? Which means I can type in x minus 5 squared plus y plus 2 squared equals 49, and it will graph that circle for me and have absolutely no problems with it. Does that make sense? Okay. If you ever use a TI 83 or 84, okay, and there's other calculators out there that are this way as well. The TI 83 or 84, when you go to graph something, you have to hit y equals to get in, basically to get the comparative input that Desmos gives you over here on the left. Notice here, it automatically sets up what y has to equal. So you cannot type in, this is called an explicit graphing calculator, which means you have to solve your equation that you have in front of you for y before you type it in. If I type x and y in on the right-hand side of this thing, it's not going to know what to do, okay? It needs you to solve for y. So that's kind of a pain in the butt to do when we have something like this, okay? It's possible, and I'll kind of show you how we would have to do this if you are a person that uses that calculator, but then hopefully that maybe gets you to be a fan of Desmos or GeoGebra. If I want to solve for y here, what we need to do is I need to first move this stuff to the other side. You guys agree with that? So I'd have y plus 2 squared equals 49 minus the quantity x minus 5 squared. Now to get at this y value, I need to take the square root. So I'll take the square root of this. So now I'll go y plus 2 equals, now when I take the square root, it's plus or minus. Now it would be all this garbage, 49 minus x minus 5 squared. And now to solve for y, I have to subtract 2. So it would be minus 2 plus or minus 49 minus x minus 5, that quantity, squared. That's a way that I would have to explicitly type into my TI calculator to get the graph of that circle. I'm going to type it in, because you would type it in the same way now that you have y equals and Desmos as you would in your TI. So I'm just going to do it here so you can see it overlap the red one that's already there. If I go y equals negative 2 plus the square root of 49 minus x minus 5 quantity squared, you see that it gave me that blue portion of my circle that I'm toggling on and off. Does everybody see that? Okay. So when I typed in that positive version, when this was a plus sign, it only gives me that semicircle. So if I type that into my TI 83, 84, it's only giving me my semicircle. I then, because of the way we took the square root and we introduced a square root, we get plus or minus. Now if I put a minus there, now you can see that it gives you the bottom half of that circle. So these two things together, the green one and the blue one, equate to that red one. The red one is referred to as, like I said, that's an implicit equation. These are explicit. Okay? And when you have a tool that is programmed like Desmos is that will address implicit equations, it is so much nicer for us. Okay? Because it alleviates having to go through all this. Okay? I'd like to show you something. I know you don't need to know this, but I think it helps with where you're going to go in terms of maybe trigonometry if you're a person who's going to take trig. Okay? If I center this thing back at 49, okay, what we do in trigonometry is we talk about polar coordinates, which would be something that looks like the graphing system ends up looking like this. Okay, instead of the x's and y's, you have a bunch of circles and a bunch of angles dividing those circles. Okay, but if I hit r equals 7 here in polar coordinates, that is, let me get back to, can I show both on top of each other? I can't. That is the same equation right there in polar than that is. And that's much easier to deal with algebraically elsewhere than this. Does that make sense? And I'll show you when you get to trigonometry, or somebody will show you when you get to trigonometry, how to get from this to that. But that's, you need this understanding that we're talking about right now to get there. But being, of course, again, not obviously going to ask that kind of stuff. It's going to be more of this type thing. Okay? Say again? You can, with this here, you can and you will see them do this eventually. If I can fact or essentially FOIL that out, right? You can expand that. So getting back to your question, you can see this, like they'll do this. They'll go x squared. So if I FOIL this out, that turns into what, minus 10x plus 25. And this one here, if I expand that, turns into y squared plus 4y plus 4 equals 49. They'll combine the 25, the 4, so that gives me 29, right? And then it just depends on where they want to put it. They might put the 29 over here through subtraction, so give you 20. So you might see it written as x squared minus 10x plus y squared plus 4y equals 20. When you look at that, you would not, so if I started you with that information there, you would have absolutely no idea whether that's a circle or what it is, right? Okay? If I gave it to you in this form here, you would have an understanding that that is a circle. Okay? Now what stinks, and you'll see this eventually, is if I make this a minus sign right there. So I'm just going to do that real quick. Make that a minus sign. It changes everything. If I make that a minus sign, so what would that do down here? It would turn all of those into minus signs, right? Okay. But let's just, if I were to kind of expand that, it would be x squared minus 10x plus 25 minus y squared minus 4y minus 4 equals 49. And if I gave you that all kind of work together, simplified, so that'd give me, what, 21, move that 21 over, so it'd be 28 here. You'd have x squared minus 10x minus y squared minus 4y. And if I gave you that compared to that, you would not know which one of those is a circle right off the bat, right? Okay, now I'll show you, somebody will show you later on in Algebra 2 how to decipher that. But if I look at that, if I graph that thing right there, let's see here. So just demonstrating that x squared minus 10x plus y squared plus 4y equals, what was it, 20, is still the circle with a radius of 5, okay, centered at 5, -2. If I put 5, -2 in there, You see that that is the center, right? Okay. Now, if I, like I said, if I changed everything and it became x squared minus 10x minus y squared minus 4y equals, what was it 28? Now you get that shape. Okay. Does anybody know what that black shape is called? Nobody knows? But it's called a hyperbola. Okay. Let me show you something with that real quick. Hyperbolas are used. Have you ever heard of something like a hyperbolic lens? Ever heard that phrase before? What happens with a hyperbola is a physical attribute of it is that we can focus light on certain points, okay, that exist inside. These are called focal points that exist on the inside of these branches of this curve. It'd be like a focal point right here and one right here. And what happens is that when light either hits this branch or that branch, the light is redirected towards those focal points. If we take a piece of like glass or mirror or some type of lens and make it hyperbolic in shape, we can redirect light to magnify things. Okay, so a lot of your high-powered telescopes, okay, the lenses in them are constructed using this hyperbolic relationship, so we can get greater magnification out of a smaller instrument. But kind of show you the relationship real quick about all these things. These are called conic sections. So a circle is what we refer to as a conic section. So let me get this GeoGebra that I built to show this. So when I say conic section, the root word to that is cone, C-O-N-E. Okay, you guys know what a cone is, right? Okay. So these types of shapes, I've got two cones over here on the left, and we call them inverted cones. Okay, they're sharing that vertex, one's on top of the other, right? Okay. If I take a plane, okay, and I intersect those cones, and right now my plane, that blue shape, is parallel to the edge of my cone, or one of my cones. And if I look at the cross section of that, okay, so this is called the cross section. Does that make sense? Okay, basically the place where that plane and the cone intersect, that shape is this shape right here in this middle window. What is that shape in that middle window? What's that look like from Algebra 1? That's a parabola. Okay. If I change the degree of which my plane intersects my cones, so let's say that I make that's changing my cones. Let's say I change the degree to being that, to where I intersect both cones. Okay. When I intersect both cones, the conic that is created is this here, which is a hyperbola. Okay. And you can see, like, we can make it more drastic and by changing the angles and that kind of thing, the position of the plane. But that may be more like the one that we saw in our equation. Okay. If I take my plane and change it to that, what's that shape? We usually say oval, right? Okay, an oval is actually not a mathematical term. We call that an ellipse. Ever heard that word before? Okay, so that is an ellipse, which is an elongated circle. Okay, so if you put your hands here and push this thing together, push your hands together, eventually you're going to come up with that there. And that is when, it's not exactly, there we go, 90. So that shape is your circle, and that's when the plane is intersecting parallel to the bases of your cones, okay? But all of these shapes, so those are 4 shapes: parabolas, circles, hyperbolas, and ellipses. In expanded form, they all look like these. They look like, because that was the circle, that was the hyperbola. If I were to give you an ellipse would be very similar to this. Basically, let's see here real quick. Let's go to, go back to Desmos. Put the circle back in. If I put like a 2 right there, now it's an ellipse. Does that make sense? But it structurally is very similar to what we had as the circle. If I put like a 5 right there, it's now going to change the ellipses. Now it's elongated left to right. That kind of makes sense? So to answer your question, will they show it in different representations? Yes, they can. Will they on the end of course exam? I don't know. So tomorrow we'll start with this here, and I'll teach you how to get it into this so that you can actually graph the circle. When you get in Algebra 2, they will spend time teaching you how to do that process that we learn tomorrow with an ellipse, with hyperbola, and it's pretty straightforward. Okay. When we look at the types of questions that you're going to see in Math Excel, they're going to ask you something like this. They're going to say, what is the standard equation of a circle? So standard equation, right now, we're just going to say is that right there. Okay. Can I plug? So if that's 3 and 5, that 3 is h, 5 is k. So we just go x minus 3 squared plus y minus 5 squared is equal to what? 36. So if they give you the center and give you the radius, it's just kind of plug and play. It's very easy, hopefully, to generate the equation then for that circle. They may ask you to do it in reverse. They might ask you to look at these and say, okay, if we look at number 25, what is the center for that circle? Okay, so the h and the k are either 7 and 5 or negative 7 and negative. We've got to figure that out, right? Okay, so it's always, your center is always the opposite of that number. So negative 7, and opposite of that number would be positive 5, right? Because the format, remember, is always x minus h, right, lowercase h. It's always x minus h and y minus k. So if it's a plus sign, then we would write it as x minus negative 7 to make that plus sign, right? So then negative 7 is the h value. Same thing for the k. What's the radius going to be? The radius is 4. What if I look at this one? What is the center for that one? 3, negative 8, and what is the radius? Radius is 10. So it's just working in reverse order, right? Okay. Tomorrow we'll spend some time working these more difficult type questions where they give you everything you need. They give you endpoints of a diameter, which isn't directly the radius, isn't directly the center, but from that information you can find the radius, you can find the center, and then plug that stuff into that formula or that equation. So we'll do that tomorrow. Do a couple of these questions up here that we skipped over as well tomorrow. No homework this evening.